Log on, tune in, find out. Another good idea from Cambridge.
Great privilege and pleasure to have a chance to talk to Anthony Hewish, who I am under the fond delusion was in the room where I now work just before I was there, which we will check afterwards. But Anthony, tell me first where and when you were born.
I was born in Foy, in Cornwall, in 1924. My father was a banker there. He was manager of Barclays Bank in Foy, in Cornwall. Lovely little port. And we left, unfortunately, before I was fully one, and went to the north coast, to Newquay, which is surfer's paradise nowadays, and a place I really don't visit very much anymore. But it was Newquay where I was actually brought up, on the North Cornish coast. I mean, pre-war days, pre-World War II, it was a very nice place. I mean, it was a holiday town, but it hadn't been spoilt by too many organisations and surfers and things. The coastline is absolutely marvellous, and I can't really think of a better place to be brought up. I went away to school in Taunton, but getting back for school holidays and long summers playing around with crabbing and all that sort of thing was marvellous.
When you mention crabbing and things, I mean, a lot of the scientists I've talked to, particularly the biologists, have got their first interest in science from wandering around watching birds or picking up shells or something. Do you think wandering along the beaches of Cornwall had any influence on your later career?
I think it may have guided us a little, but I was more interested in physical things. I mean, the sea as a background to escape to and just enjoy myself. But at home, we had rather tolerant parents, and we got away with doing all sorts of minor experiments. I mean, we used to plug into or rather we used to pull the mains leads out of the wall and get connected up and do that sort of thing. My brother, I'm the youngest of three brothers, and it was the middle brother, John. He was 3 years older than I was, and we were both rather technically minded. He was particularly interested in building model aircraft and things of that sort. And jointly we did all sorts of crazy things. I mean, the sort of thing boys do, making explosives, and I particularly tried electrolysis using the mains, which didn't help because we lived above the bank. He was manager of Barclays Bank in Newquay, and we lived in the bank house, and so we were on the first floor. And whenever we did anything crazy, it would plunge the bank into darkness beneath. So we weren't popular on those days. But that was the sort of thing. I mean, what you'd say mucking about in a scientific way is where I got my interest. I loved making things and so on, and just how things worked in general. That's how I got into it. But the sea in the background, I mean, was the escape, and just either in it or on it, rowing around, trawling, I mean, spinning for a mackerel and so on. Absolutely marvellous place to be then.
Lovely. Well, you've mentioned your father. Was there any way in which, I mean, there's no obvious link between astronomy and bank management, but was he an intellectual of any kind at all?
Not really. No, I think not. I mean, he was a Devon boy. His parents were drapers in Barnstaple in Devon, and he had a love of the country. Being North Devon, you could hardly not. And he did his early banking in Bodden in Cornwall, and was a golfer. Newquay has a lovely golf course, and he did much of his bank manager's business on the golf course, I think, as they do. But no, he wasn't in the least bit scientific or technical. He never knew how things worked and so on. So we were just born with this, I suppose, just this natural curiosity. I mean, I was always just wanting to know how things worked, and was inclined to take them to pieces until I knew how they worked, and that's how it was. And we had tolerant parents who let us do these crazy things. I mean, making explosives, which we used to take out on the cliffs after dark and let off, you know, things like that. In those days, you could buy everything you needed for a huge.
Be arrested for that nowadays.
No, you couldn't do it, but you go into Boots and buy the ingredients of gunpowder, you know, and that afternoon you could be making explosives, and so that's how we lived.
What about your mother? What sort of character was she?
Well, she was a Cornish girl, but surprisingly didn't have much liking of the sea. She was very much a farmer's daughter, and she was brought up on a farm, and one of three daughters, and she had a love of the country, but not a great deal else, if you know what I mean. She wasn't an academic in any way. One of her sisters was, and or at least, I mean, she wrote and that sort of thing. She never went to university. But no, my mother was just a nice country girl, I think, and a wonderful person to bring us up. Very tolerant, but not guiding in the way of scientific or what we did. Maybe a guiding hand about doing dangerous things like climbing cliffs, but no.
Well, you mentioned going to school. Where did you first go to school?
Well, I had my early schooling, of course, in Newquay, and was at the Newquay Secondary School for a bit, but then we got sent to King's College, Taunton. I went away to King's College, Taunton, which is a smallish public school, and I must have gone away then when I was about 12, I think. I went into prep school and all the way through, and I was there for seven years. So that was my main pre-university education.
Were there any teachers at either the primary school or at your at King's School who influenced you much, or?
Not greatly, not greatly. My physics master, Padfield, was a Keys man. He was why I went to Keys eventually when I came up to Cambridge, and he wasn't a great physicist. I mean, he was looking for jobs in the time of the Depression in the 1930s, and he was better at hockey, I think, than he was at physics, quite honestly. He was a hockey blue, and I think that's what effectively got him his job at King's College, Taunton. And but he was all right, and he encouraged and so on. But I can't say I really got great inspiration from my schoolmasters. I think it was self-generated, really. My interest. I mean, schools were much more tolerant then. You could just wander into the chemistry lab and play around with things. And once again, one made things like nitrogen triiodide. I don't know if you know that, but it ignites at a glance almost when you've made it. You just mix iodine with concentrated nitric acid, fuming nitric acid as they call it, and it dries out into a black powder, which if you have it on a paper and shake the paper, it ignites. And
this is going on to YouTube, so
so perhaps I shouldn't say these days. Well, you can't buy these things now. You need licenses to do all this. But no, I think it came really internally from inside me. Nothing sort of pointed me in any particular
there wasn't
direction.
any particular book or anything.
No, not really. No, it just came out of. I think I must have been born with it, actually.
Were your brothers at the same school?
Same school, no. My middle brother John was, and we were the close brothers. My brother Paul went into banking, but he was 6 years older than I was, you see, and that's, when you're young, that's quite a gulf. And I mean, we got on well together, but he was doing quite different things.
Did you enjoy being at that school? Some people have.
Moderately. I didn't hate it, but I mean, I wasn't wildly athletic or sporty. I mean, one had to play rugger most afternoons of the week, which I tolerated, but I didn't excel at that particularly. The pinnacle of my sporting career was getting school colours for cricket, you know. I'm sorry, not school colours, house colours. I mean, we had 4 houses, as public schools do, and I played for the house and made a few runs once and got my colours. But I didn't regard myself as any sort of sportsman. I did it reluctantly, I suppose you might say. I was happier playing around with things in the lab. And in those days, most of the playing was actually in the chemistry lab rather than the physics lab.
Was there any other hobby you had? I mean, were you interested in music? Have you been interested in music?
I am now, but that's through my marriage. That came later in life. I had the option to play the piano at school, but it was what we called a sissy thing to do in those days. I mean, young boys at boarding school didn't do that, and, so I didn't, much to my regret, actually.
You didn't sing, or?
No, not then. We had school chapel twice a day, and that was enough singing for me, actually. But I didn't have a natural aptitude for music. I mean, I played in the bugle band, you know, for what we called the OTC in those days, the Officers Training Corps, and that was a way of escaping too much square bashing, because if you were in the band, you led a slightly different life. And, but that was the pinnacle of my musical career at school, was playing the bugle in the OTC band. But you can't call that really being very musical, I think.
But you mentioned later, through your marriage, you got interested in music.
Yes, well, my wife plays the piano. She's a teacher. Well, she was a teacher, and she was quite good on the piano, and she got me going to concerts. I mean, I met her when I got back to Cambridge after the war, and it was just when I was about to start research that I met her, and we've been together ever since. And she's, as it were, led me gently into the higher reaches of music, and I simply love chamber now and opera and that sort of thing. Not so much large orchestral concerts, but chamber music where you can actually see what's going on and see people interacting with each other. And that's a great release, actually, and a big part of our lives now.
Do you think it's fed in any way into your work, music?
I doubt it.
You
really.
doubt it?
No, I don't.
The music of the spheres?
Music. No, I mean, I'm rather down to earth. I mean, I plug things in and try and get some information. I mean, I had no great aspirations to solve the riddle of the universe or anything like that. It's just that when I came back after the war, I had some electronic technology which I understood, and discovered it was going on in Cambridge, and went and began research there because it was the obvious option for me. But I hadn't planned to be an academic, I must say. No one predicted I was going to get a first in my part 2 finally.
Well, we'll come back to that.
Come to that later on, but no
music. Right. Well, let's move on then from school. You went to Keys.
Yes, I went to Keys because my hockey playing physics teacher, Padfield, said it was a college of a reasonable size, not too big, not too small, and he was very happy there. And of course there was such a desperate shortage for trained scientists during the war that you could get to Cambridge very easily, and they would fund you. And
this was just before the war, was it?
No, this was in 1943. Actually, I had well, I came up to the university in 1942.
Yes.
The war was on, and they were desperately keen to get more scientists, particularly into radio and radar. And I came up as what was called a radio bursar. They funded you, and in those days there was a 2-year course, an accelerated course, to part 2 of the natural sciences tripos. But because of my background in rowing and so on at Newquay, I spent, I think, too much time on the river in my first year. I'm desperately keen to row in an H, you know, and get that lovely feeling when everything is synchronized and so on. And I spent afternoons practicing on the river when I should have been in the physics lab. And I didn't do very well at the end of my first year. And the authority said, well, I think you better go off and do something useful for the war effort. So I was directed to the Royal Aircraft Establishment, Farnborough, after just 1 year. And I spent 3 years there until the war ended, for which I was immensely grateful, actually, because the experience, my wartime experience, I began to understand what physics and some aspects of maths were really about in a way that I hadn't realized when I was an undergraduate. I mean, I recommend people to go to university rather late in life if they can. At least it suited me. I mean, I came up to Keys when I was 18, and I wasn't really very well versed in how the world worked.
Mm.
I mean, boarding schools kept you enclosed. I mean, we weren't allowed even into Taunton. We were just in a monastic atmosphere, really, and that's not too good for one's general education, I think.
Mm.
So I was really rather immature, I suppose you might say, when I came up to Cambridge. And I should have worked harder, and I didn't, and they sent me off to Farnborough.
What was the nature of your work in Farnborough?
Initially radio communications, radio receivers and things, but I hadn't been there more than a few months before I was directed to TRE, which was the home of radar, the boffins.
What is TRE?
It stands for Telecommunications Research Establishment, but the name means nothing. It was where radar was essentially invented during the war. All the airborne radar applications were going on there. And I had the job there, not of developing particular equipment, but on training the air crews actually how to use it. My job was called PDS, Post Design Services. Having worked on the development of a particular gadget and seen it through production stage, then you went out to the squadron where it was being fitted. This in my case, this was Bomber Command, and I was involved with the device for jamming German airborne radar. And what the device did was to radiate noise at high power from the tail end of a B-17, the American Flying Fortress. And these aircraft flew in the bomber stream. And the idea was to blanket the German interception radar on their night fighters. I mean, I don't really know how effective it was, but my job was to teach the ground crews how to service it, and the air crews how to twiddle the knobs, you know, and very interesting. But not actually a design job from my point of view. I mean, I had to know exactly how it worked and everything, but I didn't design it. I got to know it after the initial design prototype had been made. And that's where I first met Martin Ryle. He was head of that radio countermeasures group, as it was called. And
how much older than you was he?
Beg what?
How much older than you was he?
He was, about 2-3 years. He was an Oxford man, and I think he must have been about 3 years older than I was.
And you worked very closely with him for many years.
Yes, he was in charge of the of developing the gear at TRE Malvern, and so I got to know him pretty well to begin with. And I had no idea actually he'd returned to Cambridge when I came around to see what research I might be involved with, but I discovered he was here, and it was an obvious thing to do. I mean, I met you couldn't be in his company for long before realising how immensely bright he was. He always thought up solutions before you did, and was a wonderful man actually in many ways.
Now, yes, I was going to ask about his character and mentality.
Yes, I mean, a very reserved sort of man, and could go off the handle rather rapidly, and but on the other hand, immensely kind and thoughtful, and I found him a wonderful person to work with.
You spend a lot of time talking together.
Quite a lot. Quite a lot.
Crick
yes.
and Watson and so on spent their time chatting.
Yes. But I mean, he was just so down to earth and natural. You couldn't help liking him.
So at the end of the war, you came back to finish off your degree.
I came back to finish off my degrees, and I was here for 2 years then. And
this is in 45. You came back.
I came back. Yes, I came back in 46 actually. 46. October 46, and took life more seriously. Naturally, it was a wonderful time to be in Cambridge because all the ex-service people were coming back, and so you were in the company of people you'd been with. I mean, not necessarily personally, but the types you'd met during the war. The post-war years were sort of legendary. If you talk to tutors who are still alive now, they wanted to learn. They worked hard. They didn't play around. I mean, partying didn't really exist in those days, and they were just wonderful people to talk to. I mean, you talk to people who had been in fighter pilots and that kind of thing. Cambridge was a very interesting place, but I didn't naturally find physics easy. I mean, I'm not. Mathematics doesn't just flow into my head. I have to work rather hard to find out what it's all about. But after the war, I realized what the mathematics was doing, things like Fourier analysis. I saw the power and point of it, because this had been used in my wartime experience. And so I came back much wiser, and I spent less time on the river. In fact, I spent no time on the river when I came back. And I worked quite hard and ultimately got a first. But that was again partly due to my wartime contacts, because the man who was running radio physics at the Cavendish lab, Jack Ratcliffe, who's with us no more, I'm afraid, he was a research student with Edward Appleton, who discovered the ionosphere, and there was a strong tradition of radio physics here in the Cavendish. And Ryle had gone to work with Ratcliffe after the war, and as I said, when I had the chance, finally, I got my first, and Ratcliffe had been a very influential teacher to me. His courses on electromagnetism were legendary, and he was one of the big influences. I mean, I really got to grips with electromagnetism on the practical level, and when I found I could do research in that area, in Ratcliffe's group, Ryle was then not group leader, this was an obvious thing for me to do, so that led naturally through. But I hadn't planned to be an academic, I have to say. I'd got jobs lined up, but my tutors, after I'd been, this was in the summer of 1948, they said, have you got a job yet? Because don't make up your mind too quickly. Keep your options open for a while. This was before the results came out. They knew what the results were, but I didn't. and I got a first, much to my surprise. Although I had worked hard, it wasn't a total surprise finally, because I was getting to grips with things. And but I hadn't planned to be an academic. But when I had the chance to do research, and I discovered there were interesting things to do, for which I was fairly well equipped, and together with that, I'd met my girlfriend in Cambridge, who was teaching, and that was a nice thing to stay on in Cambridge. So everything clicked and came together, and that's how I got into research.
Radcliffe, you said he influenced you. Was he your tutor or your...
No, but he gave
lecturer?
Excellent Part 2 lectures in electromagnetism, and everybody speaks very highly of his teaching abilities. And I met him. He was, in fact, head of the post-design services group at TRE Malvern, and I'd interacted with him during the war, so I already knew him, you see, and so he was a big influence, I think one could say.
Were there any undergraduates at your time? I mean, any people who you've remained friends with or who have influenced you in any way?
What, since then, you mean?
Yes.
When
I mean, do you have any famous compatriots, or whatever the word is?
Famous compatriots. Well, in radio astronomy, I think, well, people like Graham Smith, of course, who's still alive. He was a colleague at TRE. He was a year ahead of me at TRE, and
did he come back to Cambridge?
He came back to Cambridge to do research. He'd done a rapid 2-year course, so he was fully qualified, and he was working with Martin Ryle. He joined Martin Ryle began research in 46. I began in 48, and Graham Smith had joined in 47, so that he'd been doing research for a year when I arrived. But it was a sort of family affair, and it was picking up wartime connections in a sense. And radio astronomy, I mean, no one knew what it was going to... It was a continuation, in a sense, of our wartime work together, because no one knew that it was going to open a new universe to us. We were just playing around with the technology we understood, investigating these strange radio waves from the sun initially, because that was a wartime discovery, radiation from the sun. That's how radio astronomy began in this country.
Who made that discovery?
That was James Hay, who was a wartime radar man.
Is that with an A-Y or
H-E-Y?
E-Y.
He discovered radiation from the sun. He was with operational research with anti-aircraft, and on one day the anti-aircraft radars were swamped. This was in February 1942, just after the pocket battleships had made their dash through the channel. And it was thought initially to be some sort of new secret weapon of the Germans that's blinding our radar. Turned out to be coming from the sun. He realized that when he discovered that all the radars that had been blanketed were picking up radiation from a certain direction. It was a dull day, rather like today. And he phoned the Royal Greenwich Observatory to say, was there anything funny going on with the sun at that moment? And they said, well, it just so happens there's an active sunspot right in the middle of the disk. And so that clicked. And that was a secret wartime discovery then. That was 1942.
Mm.
But Ryle thought this would be a good thing to investigate when he got back to do research in Cambridge.
Mm.
And so that's how it began. But then, of course, radiation became known from other directions too.
Mm.
And I got in on the ground floor, as it were, just when that was beginning. So I was extremely lucky.
What was the theme or thesis of your thesis, so to speak? What were you particularly studying in the PhD?
Well, this may sound a little odd, but it wasn't astronomy for its own sake. What I had discovered in about my first year of research was that radiation from these few, what we now know as radio galaxies, but we called them radio stars in those days, the radiation fluctuated in time, and it wasn't clear whether this was an intrinsic variation of the sources themselves, or whether it was a propagation effect, whether the radiation was being affected on its traverse through the upper layers of the ionosphere here. And Graham Smith had already made measurements which suggested that it was an ionospheric effect, and I took that up and confirmed that in fact the fluctuations were caused by mainly nocturnal disturbances in the ionosphere. It was my initial research that led to the discovery that this only happened at night, this fluctuation of the sources. And here's a jolly good way, actually, of using extraterrestrial radiation to probe the atmosphere at heights which were then unreachable by any other method. And because the astronomical side hadn't really developed, the mystery of what radio galaxies were, I mean, the term radio galaxy didn't come for several years because we thought these were stars in our own galaxies, like the sun. I really got diverted to using radiation, extraterrestrial radiation, to study the upper atmosphere. Jack Ratcliffe, who was an ionospheric scientist essentially, was keen, in fact, that I did this, and he gave me great support. And in my thinking about this, I developed a bit of theory which pleased him a great deal, and I sort of latched onto this as my own particular research area. It's nice when you're a graduate student, you know, to have something that you can call your own. Martin Ryle was so bright that he'd thought of all the clever things to do weeks before you could think about it. But here was something which I could develop on my own, you see. And so I got on with that, and that was what my thesis was all about, in fact, using radiation from what we now call radio galaxies or supernovae to just as a source of radiation from outside the atmosphere, and investigating the fluctuations and what they could tell you about the properties of our own ionosphere at heights of 100, 200 miles. And measuring wind speeds, for example, up there. I was the first to measure the speed of an ionospheric wind in the upper atmosphere, upper ionosphere, and that gave me a great thrill. This was research I could manage on my own with not a great deal of technical requirement, actually. It was quite elementary, the radio telescopes technology that I was using, very, very simple. But it was all brand new, and so you couldn't help but make good discoveries and publish papers, and that's just what you need, isn't it, as a starting graduate student?
Where were the radio telescopes? This is before the arrays and so on.
Absolutely, absolutely. We were using wartime surplus equipment up there.
Where was it? On the top of the
This-
Cavendish or something? Or?
No. We had to get outside Cambridge because of ignition, automobile, car radios and things. I don't mean car radios, I mean car electronics, spark plugs and things cause a lot of electrical interference. So we were just behind the rugged ground up here, just behind the University Library, what we call the old rifle range, still called the old rifle range. And with wartime surplus equipment, that's how Martin Ryle began, and that's what was there on site when I joined up. I built my own primitive radio telescopes to do my own particular jobs, but they were only little bits of wire strung between poles and so on, the sort of thing you could build in a week or two. And once again, this was the sort of thing I'd been doing as a child, playing around, you might say, almost, with stuff that I could handle and make myself. And that was the joy of it in those days. And you could make very nice discoveries with very simple basic apparatus. And
this is the sealing wax and the
sealing
strings.
wax, as you say, string and sealing wax, the true Cavendish tradition. And the giant radio telescopes, of which I was connected, actually came along later.
And it again shows your hands-on interest. I mean, that you liked making things.
Yes, indeed. This was, yes. I mean, it didn't cost a lot of money. This was research that you didn't have to fight for funding. I mean, we had enough funding in the Cavendish to support the sort of work I was doing, so I didn't have to write research proposals. All I had to do was to consult Martin Ryle and Jack Ratcliffe and say, look, this is what I like to do. And they would think a bit and say, yes, that looks worth doing. Go ahead, and in a week or two you'd be starting. Nowadays, of course, it's a very different world, and you have to sit on committees and so on and justify yourself. But in those days it was done more or less with personal contact, and we had the cash. And they were golden days in research because you could do your own project, get on with it, and within a year have really broken new ground, and I found that immensely satisfying.
When did you first become aware that very close to you a new machine for analysing your results had just been invented? In other words, Wilkes's EDSAC computer.
Oh, right from the beginning, actually, because Martin Ryle, as you know, was famous for his discovery of his invention of aperture synthesis, using radio telescopes, simple telescopes in different positions, and adding up the data. Essentially, you're Fourier analysing the sky, and you need a computer to analyse the data. And the work that was going on, Martin Ryle in the very early 1950s was experimenting on using EDSAC in its earliest form to analyse the data from the simple interferometers he was then using to make simple maps of the sky. And so we were aware of EDSAC right at the very beginning. It was of no help to me to start with, but later on I got very involved with it because someone had to do the early programming, and that fell to me. But I didn't use actually computers in my own work at all. I just didn't need to. And recording with computers, I mean, there was no. We were recording with pens on paper, like electrocardiograms, and I mean, the digital world just hadn't begun, as I'm sure you realise in the early 50s. It just wasn't there. But we were very conscious of EDSAC, and Martin Ryle had his eyes on it, and we were using that from the very beginning.
Were you aware of Alan Turing at that point?
No. I only read about Alan Turing later. I just didn't know of his work, and I didn't know about Bletchley Park or anything.
That's interesting. So, going on, after you'd finished your PhD,
Yes.
what did you then do?
It just developed in a natural way, where I had worked originally on the ionosphere. We then discovered that radiation passing through the sun's atmosphere, radiation passing by the sun, was similarly affected. The phenomena were rather different, but having had the background of working on ionospheric disturbances, I then began to study disturbances in the solar atmosphere, and my work naturally extended out towards the sun, and it developed into studying what we now call the solar wind as measured by spacecraft, this outward expansion of the sun's atmosphere. The sun's atmosphere literally blasts out through interplanetary space at speeds of typically 300 or 400 kilometers per second. That's millions of miles per hour. But this solar wind became known when space research began, and before that era I was studying, I didn't know it was a wind, but I was just studying the solar atmosphere as it left the sun, and that kept me busy for the early 1950s. Actually, the sun's atmosphere can't be seen optically with instruments except a total eclipse, and total eclipses don't happen very often. To have a means of detecting anything to do with the solar atmosphere any day of the week, as it were, was a useful thing to do. And I tracked the solar atmosphere and studied irregularities in it and how it behaved almost out to the halfway between the sun and the Earth. And that kept me busy. For my own personal research, I got quite a lot of papers out of that, research publications. And at the same time, I was helping Martin Ryle in the design of his radio telescopes, the really big ones, which made the first groundbreaking sky surveys in this country. So it led naturally on, and so I had the two things. I was working with Ryle on the design of radio telescopes and doing my own research on the solar atmosphere.
It's not absolutely clear in the accounts I've read as to whose idea it was to space the array, the telescopes far apart.
Oh, well, that was Martin Ryle, totally Martin Ryle. And I mean, Martin Ryle's work went hand in hand with the development of computers. When you're analysing the data from these multiple interferometers, which perhaps I should explain, you can synthesize a radio telescope that you couldn't possibly build. I mean, Bernard Lovell, as we all know, was designing a 250-foot dish, the famous Lovell telescope at Jodrell Bank. But Martin Ryle was a little bit scornful about that, because he said, well, it hasn't got anything like the power that we really need. What you want is a telescope a mile across, not 250 feet. And the way to do that, and this is the reason why he got the Nobel Prize, was to make smaller dishes which are easy to build and not too expensive, and pick up the data sequentially when these are in different positions, and then you can synthesize all that in a computer to reproduce exactly what a mile-wide bowl would actually do. And that was Martin Ryle's bravery, you might say, his courage in realizing that you could actually do this, and going ahead and doing it in a big way, using computers as they developed to do the computations. And Martin Ryle's telescopes elaborated as the computers elaborated. But I was involved not so much with the computing side then as with the design of the Martin Ryle's telescopes that he used for the synthesis.
They were on a railway line, I think I've seen them. Eventually, not at this point.
They were on a railway line.
Why
yes.
were they called Mallard, the observatory?
Well, Mallard was kindly provided the money needed to move our work from the old rifle range, which we mentioned, close to Cambridge, to the new site at Lord's Bridge, which is only a few miles away. But Mallard gave us £100,000 to set up essentially the Mallard Observatory. That is to say, establishing the site and the buildings on it, and some funding for the radio telescope, but mostly the funding for the instrumentation came from what was then called the DSIR, the Department of Scientific and Industrial Research. That was government funded, the equipment. But Mullard provided the infrastructure, you might say, for the site.
You often mention, or you do mention in little bits you've read, the word scintillate or scintillation.
Yes.
Can you explain what's the importance of scintillation is?
Yes, scintillation is a grand title for twinkling. All stars twinkle, and scientifically we call that scintillation. What happens is that I mean, we've all seen stars twinkle, and stars twinkle because the upper atmosphere, even on the clearest nights, has air in it of varying wind speed and varying density, and there are clouds of different temperature and density up there, even on an absolutely clear night. And the radiation coming through is bent in different directions. And so looking through the Earth's atmosphere is a little bit like looking through a crinkly bathroom window. The radiation coming through is refracted in different angles, and what you pick up isn't a pure, undisturbed wavefront. It's waves coming in different directions essentially, and that causes this twinkling phenomenon. And it's the same in radio astronomy, except the physics is somewhat different. But scintillation is just the name given to these fluctuations, and so sources scintillate when you observe them through a disturbed atmosphere.
Thank you.
If that helps.
It does help, yes, indeed, in layman's terms. When did you first, or where were you at this point? I mean, physically, were you in the old Cavendish?
We were in the old
Was
Cavendish
radio astronomy already at the top of Colloid Science Building at this point?
Yes.
So you were already in the room which I keep alluding to.
Yes.
By this time,
indeed.
In the 50s, you were there.
Yes, indeed. I mean, we were there from the earliest days. I mean, in my case, from 1948 until
74.
70. Well, in fact, it was a bit earlier than that. 71, 72. I think, can't remember. 72, I think, was when we actually moved to our new site. But we were in those offices.
Wonderful. Oh well, we'll visit them later. Let's begin to move on towards those times. What did you then work on, moving now into the 60s?
When we had discovered that the sun's atmosphere, it was an extension of the work I was talking about earlier on the sun's atmosphere. I did a calculation in 1952, which seemed to me to rule out the possibility that you'd ever see scintillation caused by the solar wind. The reason being very simple, that in those days, when we had a handful of extraterrestrial radio sources, a mixture of supernovae and radio galaxies, they all had a rather large angular size, rather large to an astronomer, that is. The radio galaxies we were looking at then had angular sizes of several minutes of arc minutes. They were about the size of a crater on the moon, to put it in a visual analogue. Now, I had calculated that you would never see twinkling through the solar atmosphere because the sources were much too large to produce a twinkling phenomenon. To go back to what I was talking earlier about stellar scintillation, stars twinkle but planets don't. The moon doesn't twinkle because it has a much too large angular size. Any twinkling is blurred out by the size of the moon or planet. Planets don't twinkle either, not usually. And the reason is, as I've just said, because they subtend too large an angle. And when I looked at the calculations of what the solar wind was doing, I realized that you would never see scintillation because the sources were much too large, the radio galaxies and so on that we then knew. And so I never bothered to look for it. A great mistake, which I may elaborate on later on. But we discovered quite by chance in 1964 that in fact some radio galaxies in the sky did twinkle. It was a mystery, first of all, as to why they should, but a graduate student noted that they twinkled when they were not too far away from the sun. They never twinkled when they were seen at a large angular distance from the sun. And I was talking about, Martin Ryle and I were discussing this. We used to have Saturday morning discussion groups, and he said, could it be that this is a scintillation? And I went back to the books and said, well, it could be if they were incredibly small angular size. Now it turned out that the ones that twinkled best were the ones which by then Jodrell Bank had discovered were in fact rather small. And so we said, well, let's do a proper experiment and see what's going on here. So with a colleague I set up an experiment at our observatory at Lord's Bridge, and we discovered, yes indeed, a lot of the radio galaxies twinkled in fact. And this then opened up the whole field of what I called interplanetary scintillation. Certain radio galaxies, we now call them quasars, but we didn't know in those days what quasars were. The term had scarcely been invented. But if you looked at studied quasars, then they twinkled as observed through the solar wind. And so my work, which I'd been doing in the ionosphere and in the solar atmosphere, suddenly extended, and I realized that I could use this twinkling of certain radio galaxies to measure the speed of the solar wind, which was then enormously interesting because it had just been measured by the first spacecraft. I think it was the Russians who did this. They launched a Lunik, I think they called it, and I'm now talking about the late 60s. They had discovered that the solar wind existed in space. And I said, right, I'm going to measure the solar wind on the ground. And that's when my research took off. And I set up a grid of radio telescopes across England. Well, in fact, I started off with 3, one in Cambridge, one on the East Coast, and one, in fact, the other side of Thetford here. And I successfully measured the solar wind from the ground, and I thought that was terrific fun because here was this this scintillation pattern, the pattern of radiation intensity sweeps over the ground, and it was crossing England at a speed, as I said, of about 300 or 400 kilometers per second. But I could just measure the delays as this pattern crossed my different radio telescopes, and I rapidly got graduate students to help, and we measured the solar wind on the ground in competition, as it were, with the earliest spacecraft. And I thought, you know, here am I doing this for a few hundred, well, £20,000, whereas you it's more like 20 million if you 20 million pounds if you do it from space. And I spent a lot of time then, I mean several years, measuring the solar wind from the ground, and that was enormous fun. And we could do better than spacecraft in a certain sense, that you could measure the solar wind coming from the polar regions of the sun, which spacecraft didn't manage until the 1990s, actually, quite recently. And we found the solar wind was coming off the solar poles faster than it was blowing off the equator, and that was a nice discovery. But it was just at a straight extension, really, of what I'd been doing before, but applying it to the solar wind, which took my research into the 1960s, and which eventually led on to, in a natural way, to the pulsars.
Well, can you provide that link on to the pulsars at
The
this
pulsars,
point?
yes.
Is that the next story?
That's the next story. Well, I developed the interplanetary scintillation technology. I use that as a tool to measure angular sizes of radio galaxies. I can't go into the details, but essentially the scintillation varies strongly as you look at a particular source. When it's close to the sun or whether it's far from the sun, you get much more scintillation when it's near the sun than when it's far away. And if you apply diffraction theory to that, you can see that this is a method for actually measure angular sizes with an angular resolving power, which is much, much higher than you can get with any sensible radio telescope. At the wavelength I was observing the scintillation on, I could get in principle, an angular resolving power, which would otherwise require a radio telescope bigger than the diameter of the Earth. With interferometers, you can get very high angular resolving power, but with scintillation, you can do very much better. And I thought, well, we were then beginning to understand more about quasars, and in Martin Rao's surveys of the sky, 1,000 or so radio galaxies were then known, the positions of them, but it wasn't known really what the radio galaxies were. But quasars had been discovered, one or two quasars, which have the property that they have a very bright nucleus and they send jets in different directions, and they do have they have components which are a very tiny angular size, and it is those components that twinkle. And I thought, well, let us carry out a sky survey to see which of the 1,000 radio galaxies are the most interesting ones astrophysically, which are the quasars of this 1,000. Now, I could do that by seeing which ones scintillated most strongly, and I could actually measure angular sizes. I developed the technology then, the theory of the scintillation, to use this twinkling in the solar wind to measure angular size quantitatively. And I set up a survey to do this for about 1,000 radio galaxies. But it required a very unusual instrument. It had to be sensitive to see enough radio galaxies. It had to be working on a longish wavelength, which is where the twinkling shows up best. And it wasn't like any existing radio telescope. So essentially I had to build my own telescope, which consisted ultimately of 2,000 dipoles spread over a 4-acre field. And it observed the radio sources as they crossed the meridian. And according to how much or how little they scintillated, I could measure the angular sizes and sort out fairly quickly which ones were quasars and therefore deserving of further studies, and which ones were just sort of standard radio galaxies, you might say. And so I set up, I planned a survey which was operating actually in 1967. I planned it in 1964-65 as an extension of the work I've been doing, just to make a complete sky survey of scintillating sources, and to sort out the quasars from the non-quasars. And it was during that survey that the pulsars turned up. But this was a telescope that we could build with our own effort, not too expensively, on the site itself. I mean, in present day funding, it would have cost about £1 million, I suppose, or something like that. In those days, it cost about £20,000. £500,000 would have been more like it. But this was something we could get on with our own effort. Once again, you could persuade the committee quite quickly that this was worthwhile doing, and I got the funding within 6 months, and was planning the telescope in 65, and it was completed in 67, and that's when the sky survey began. And with that technology, with that instrument, it was impossible really to avoid detecting pulsars. They were just tailor-made. I mean, the instrument was tailor-made to discover pulsars because the fluctuations of pulsars are in just the same time scale as the scintillations I was looking at, so you had to see them. And that's what happened.
I always tell people that the message came along a wire which came in through the window of the aforesaid room in Colloid Science. Did it come along a wire from the computer into the room?
We weren't using computers at all, as a matter of fact. It came along coaxial cables.
Oh, cables, yes.
And it went onto pen recorders for reasons of economy and also speed. Digital recording of the quantity of data that I was handling then, I was handling a large quantity of data, wasn't really a very practical solution.
So it
was quicker
pen.
and cheaper to have pen recordings, and so we had initially 3, later 4 paper charts, just like electrocardiograms, and it was my industrious student Jocelyn who had the task of analysing all these paper charts, and she, as I'm sure you know, was the first to actually see something strange going on these paper charts.
Can you remember what she said? She said, "I see something strange, Anthony," or what did?
Well, it's actually it's a slightly longer story than that. Popular science says she suddenly saw pulses, which isn't true. What we saw was a source which was showing. Initially, she pointed out to me a record. She says, here's a source that looks a bit funny because it's showing too much scintillation in the middle of the night. Now, in the middle of the night, you're not looking through a dense part of the solar wind. You're looking in the and the solar wind, of course, its density varies inversely as the square of the distance from the sun. So when you're looking backwards, as it were, from the Earth, you look through a much less dense region of the solar wind. And normally, our radio galaxies, whatever they were, only scintillated at about the 10% level. And what she noticed was that there was a rather faint source scintillating at the 100% level. This was evident from the sort of recordings we took. I mean, you only needed to glance at it to see that here was something a bit unusual. What is it scintillating 100% in the anti-solar direction? And we didn't know what it was. We didn't know whether, first of all, it was even a genuine signal. But after it had reappeared, we surveyed the whole sky roughly once a week, and it had appeared 2 or 3 times. Sometimes it wasn't there at all, which was another mystery. And neither of us fully believed that it was a genuine source. But I said, well, let's have a closer look. It could be something like the initial radiation from the sun, which was discovered by Hay, as we've mentioned earlier. Perhaps there are radio galaxies, perhaps, I don't mean radio galaxies, perhaps there are stars in our own galaxy, which are a bit like the sun, but a bit further off, which occasionally show fluctuating signals, radiate sort of intense noise when there are sunspots on them. I mean, the sun isn't a particularly unique object. There are lots of stars like the sun, so you'd expect to see more like that. And but I realized that the radiation that we would get from such a source wouldn't look like the normal interplanetary scintillation. So I said, we've got to get a closer look at this and run a fast record and see, in fact, have a close look at those scintillations to see just what is the time structure of them. And so that's what we did. And that's how the pulses turned up. It took a little while. It took 2 or 3 months to get some good recordings. But when we looked at the fluctuations more closely on this peculiar source that Jocelyn pointed out to me, then it was clear that they were pulsing, and that was a shattering blow, really. What on earth could be doing that? It was clearly well, we discovered pretty soon it had to be beyond the nearby stars, but not too far. It was way out in our own galaxy, but it was a stellar source, and all kinds of thoughts went through our minds.
Yes.
I mean, it was such an artificial signal that I had to seriously consider: is somebody actually sending a signal to us? It didn't seem to be coded in any way, but It wasn't impossible by any means. And we could measure the size of the object launching the signal. It couldn't have been larger than a planet. So we had the problem, regular flashing signals from an object which is of planetary size or less. And what on earth can it be? And
how close were you to breaking this news to the ever hopeful press that you had discovered little green men?
Very wary not to do that.
Yes.
We kept our mouths tightly shut because we'd already had our fingers burnt this way. Way back in 1957, we were the first group of radio astronomers to locate the Russian Sputnik. Everybody knew it was up there because you could hear it bleeping, but nobody quite knew where it was. And we set up a simple interferometer. I wasn't involved with this particular work, but we set up a simple interferometer here just at the old rifle range, just a few miles away from where we're sitting, and got the rough orbit of the first Russian Sputnik. And the press descended in hordes on the old Cavendish, on the rifle range there, and filled the lab, asking stupid questions and tripping over cables, and normal work was quite impossible. And that was just confirming that the Russians had actually sent up a satellite, and where it was, an Earth orbiting satellite. And that attracted hordes and hordes of the press. They couldn't detect it at Jodrell Bank because they didn't know where it was, you see, and it crosses the sky in about 90 minutes. And if you've got a 250-foot dish, you know, to hunt around, you just can't catch it. And but when we sent the position to Jodrell Bank, they picked it up immediately. And then the press, of course, all got in their cars and went off to Jodrell Bank. But the point was, here we had a real mystery at Lawson Bridge. And the moment anything leaked out that we were picking up something strange, possibly even intelligence, what would have happened? The place would have filled instantly with the press. I mean, you couldn't have avoided it. And I was dead keen myself that we should get on with the science quietly and deliberately without being bothered by people asking stupid questions and getting it all wrong and blazing publicity all over the world. I had a test for checking the little green men idea. I had to pinch myself actually to really take this seriously, I admit. But I was made to think seriously about this by, I don't know if the name Teddy Bullard means anything to do, the late Sir Edward Bullard, a famous geophysicist. It was a bit frustrating for me in these exciting days because I had to spend a week closeted in my room in Churchill College marking the scholarship exam. we had an open scholarship exam in those days, I'm sure you'll remember, and these had to be marked quickly and immediately, and that meant the full-time work for about a week marking scholarship papers, and that was almost directly after the first pulse had actually appeared on the records. The first pulse appeared on November the 28th, and the scholarship exam was about the 1st of December, so I was very busy, tied up in Churchill College, and I was having lunch there one day, and sitting next to Teddy Bullard, and I quietly mentioned to him the fact that we were picking up these unusual pulses, and what did he think about it? And he said, well, if they're narrowband, they're probably intelligence. Very wise remark. And so he took it seriously, and I had to take it seriously. And we were, in fact, already measuring the bandwidth, and they were indeed narrowband signals instantaneously. But my argument was that if you have intelligent signals, they're likely to be coming from a planet, and a planet has to be in orbit about a star. So by then, working in my room in the old Cavendish and doing careful timing of these pulses, I'd already discovered that they were keeping time to better than a millionth of a second per day, and I realized that I could detect planetary orbital motion very quickly if they were coming from a planet in orbit about some distant sun. And so I set up measurements to do that. I timed the pulses accurately for, well, I did it in the end for just about a month. But I decided that if I could detect this planetary orbital motion using what we call the Doppler shift, as the planet accelerates towards and away from the Earth, you can detect that by what we call the Doppler shift by careful timing measurements. And I set up timing measurements and carried these out myself for several weeks, and ultimately discovered that the only orbital motion present, there was a huge orbital effect which turned up immediately, but that of course was the Earth itself in orbit about the Sun. That produces a big Doppler shift in the timing of the pulses. Having subtracted that out from the data, there was nothing then left, or if indeed there was orbital motion, it would have to be in an orbit so distant from a star that life as we know it wouldn't have been possible. And that took me, as I said, the first pulse was about November the 28th. I was doing Doppler shift measurements from the first week of December. I think I started about December the 12th, 11th, and I did that right through December until early January. And it took me that time to prove that there wasn't any additional Doppler shift apart from the motion of the Earth. That eased my mind quite a bit, because it's not physics anymore. If it's intelligence, it's a different line altogether. But at the same time, Jocelyn had been analysing past data, because it was likely that if we discovered one, there were others of these sources on the charts. And she came up with 3 others, which eventually she checked, and they turned out to be pulsars too. So it would perhaps be a bit unlikely that you'd suddenly start picking up intelligence from various directions in the sky, intelligence signals, but not necessarily so, because, I mean, if it's there are lots of planets around. So anyway, my mind was a little bit easier at that stage, but I had discussed with Martin Ryle before Christmas, when I didn't know the answer, what on earth are we going to do with this data if it turns out that intelligent signals are a likely explanation? And you can't just publish it, and you can't just release it as a news flash. We thought we'd work through the Royal Society in London, actually. We'd inform them and get them to consider it, and perhaps have some national statement about this. But it was too big a thing to be handling on ourselves. And should the evidence have been pointing towards intelligence, we would have then, without making it public, approached the Royal Society and say, here, we've got this, what do you think we should do with it? Luckily that never happened, because by about the first week in January, as I was saying, I had found no Doppler effect for planetary motion, and Jocelyn had come up with 3 others. So we then started to hunt for scientific conventional explanations, and I went to the library and looked up books on midget stars and so on, discovered that white dwarfs and neutron stars were possible solutions, and we had enough to write about without saying what they were, but I mean, just describing the work that had been done was quite a lengthy job, and I wrote a lengthy later letter about all this, and hinted at the end, plausibly, this could have been oscillations of a white dwarf or a neutron star, and we left it there. But of course that was when the balloon went up, and we kept our mouths tightly shut, for which the Americans criticised us roundly later, but I don't repent for a second.
Why
I gave
did
a
they
lecture
criticise
in the old Cavendish, because I felt it was unfair to local people not to hear about it from the horse's mouth out of the world, rather than read it in the scientific press. That isn't right, because people knew that something had happened. but they didn't know what it was that had happened. I mean, half a dozen of us knew, and so I gave a seminar in the Cavendish. It was meant to be a group seminar for about 30 people. It turned out to be more like 100 because the grapevine worked and people like Fred Hoyle were there. And I gave a seminar which let the world know what was going on.
Which room did you give it in? Do you remember?
In the Maxwell Lecture Theatre,
Yeah.
which I knew well from my undergraduate and my early teaching days myself. A lovely room to give a lecture in.
Exactly,
Actually.
yes. And it would fit 100 people in.
Oh yes, yes.
Just in passing, on that one member of the audience who was there, Fred Hoyle,
Yes.
what were your relations with Fred, and how can you say anything about him? The bluff Yorkshireman?
My relations with Fred were quite reasonable in those days. I'd met him on committees. He was a wonderful person to listen to when he gave a lecture. He'd always had something interesting to say, and there was a lovely institution then at the old observatories, which is now called the Institute of Astronomy. When there were seminars with a lovely English tea laid on by the astronomers' wives. It was really old-fashioned, and you had thin brown bread and butter and slices of homemade cake before the seminar, which always actually attracted a good audience. It was a sensible thing to do if you wanted to publicise your work and so on. But whenever Fred Hoyle gave a talk up there, the Observatory Club it was called, I've just remembered, whenever Observatory Club had meetings, they were always full, particularly full when Fred was speaking, because he always had something new and interesting to say. You didn't always believe it, but it was a bit of a, he was always good fun to listen to. And he raised a very pertinent question. He was about the first to raise a question from the audience. He was sitting in the front row in the old Cavendish. And he said, well, what you really want is something in between a neutron star and a white dwarf. Now, I won't go into the reasons why he said that, but it was a very sane and sensible remark, actually. It's to do with the densities of the stellar density. A neutron star would have really given rather more rapid flashes, and the white dwarf rather too slow. And he said, what you really want, something in between, which was actually a very sane, sensible remark. But after my lecture, the positions were, Jodrell Bank knew of the positions. We told Jodrell Bank, and they got onto it straight away and confirmed it instantly, and did things that we couldn't do because they can track it across the sky. We could only see it as it crossed meridian for 2 or 3 minutes, a few minutes each day.
And you announced it formally in a paper, a joint paper in '68.
In Nature. Yes.
In Nature in 1968,
yes,
with five people's names on it.
Yours
first.
Yes. Then Jocelyn, my student. Yes. And then the others who'd been involved with the follow-up work.
Martin Ryle as well?
He wasn't.
No,
he wasn't on that.
No.
Scott, actually before Scott and Collins. Paul Scott, who's still doing radio astronomy, he's retired, living in Cambridge now, but it was confirming our signals on another radio telescope at Cambridge, which was an important part. And the Nature letter actually discussed quite a lot of work from observations not just made with my array, but with telescopes at Lord's Bridge. I mean, we went into quite a lot of theory and to get the distance measurement and so on. There was the rate of frequency drift, pulse dispersion. I won't go into the details now, but it was rather hectic 2 or 3 weeks before Christmas when a lot of people were doing slightly different things at Lord's Bridge, and to condense that into a readable Nature letter and name the people who were responsible for it. That was my job, and Paul Scott was in charge of the other observations. No, I'm sorry, there wasn't John. There were 5. John Pilkington. I've forgotten John. Pilkington.
Oh, Pilkington.
Yes,
yeah.
yes. So there were various bits of work to describe, and that's why there are 5 names on the Nature letter. But it was published within about 2 weeks, I think, which was a pretty good record for Nature in those days. So it wasn't kept secret from the world for very long. But I think that was the right thing to do. I mean, I don't think I would have handled that differently. The Americans said, oh, you should have told us much sooner and all that sort of thing. But they were jealous.
You may or may not want to comment on the sequel, which is the Nobel Prize,
Yes.
1974, because
Yes.
you must have been enormously pleased and excited to get it with Martin Ryle, but as you know, it led to a lot of controversy.
Yes. Yes.
As I understand it, the Nobel Prize was for both of you for your general spread of work, of
Yes.
which Pulsars was one part of your
Yes.
work, and
Yes.
Martin's was different work.
Yes.
And that is the reason why Jocelyn wasn't part of all this. Is that roughly right, or?
Yes, I think that's right. I mean, when I look back on that, Jocelyn was an excellent student in the sense that she was a really hard worker. She was very well organised, and to keep up with the flow of paper coming from the pen recorders was quite an achievement. And she was very good in the sense that she'd put a lot of effort into constructing the telescope. She was not afraid to roll up her sleeves and do hard practical work under rather unpleasant conditions occasionally at Lord's Bridge. But when it comes to the design of the experiment, just what observations to make, and the follow-up work, I mean, she did the record analysis very well, but she didn't initiate in the sense that she set up anything herself. She was acting really under my instructions all the time, and I think another student would have done just the same. We get jolly good students in Cambridge, and what particular aspect of it, she was sharp and diligent to notice there was something going on in the first place. But when it came to revealing the first pulse, it was my suggestion that it could be like the sun, and we got to look and see, and set up faster recordings of the different equipment. I mean, she didn't carry on to do that by herself. She did it under my advice. And so, I mean, if you have a ship of discovery sailing, it's normally the skipper who gets the credit. It may not always be correct, but it wouldn't be the lookout on the masthead. Do you see what I mean?
Yeah, yes, I do. And
it's a question of being the creativity and the insight that's gone into the science and the suggestions.
Well, it was part of the animus of the occasion was the timing. I mean, this was the height of feminist interest in the university and elsewhere.
Yes.
And it also had a kind of a rhyming effect with the Rosalind Franklin
Yes.
business. So, you know, there were various things which... But
Well, feminists do tend to pounce on things like this, I'm afraid, sometimes rightly, sometimes wrongly.
what was... You can say this off the record, but what was Jocelyn's own relationship to you after this?
Fine.
She never wrote and said, I should have had the Nobel Prize as well.
Absolutely not. And she's on record as saying that she doesn't think that she ought to have had.
Yes,
I mean, she's done extremely well since, but
she was just a graduate student.
she was a jolly good graduate student.
Right. Well, after this enormous excitement, what then did you do? The rest of life seems a bit drab after that.
Well, it branched off into different directions. I still had solar wind measurements going on at the time of this sky survey, which led to the pulsars, and that continued for a while. And I got a couple of theses, graduate students writing theses on that. But one of the features that we discovered during the scintillation, the sky survey of scintillation, is that when you look at the scintillation on we were using actually about 900 radio galaxies in the sky. We were observing 900 radio galaxies in the sky in a period of 24 hours. We discovered that certain patches of the sky showed much more scintillation than other patches of the sky over our 24 hours, and that these changes changed from day to day. And I realized then that we were actually making maps of interplanetary weather in a certain sense. The scintillation wasn't absolutely constant. I mean, the solar wind is always varying, and the density of the solar wind is varying from one day to another. And I realized that you could use these galaxies, the data we were getting, to essentially measure space weather, analyze space weather on a day-to-day basis, and make maps of disturbances in the sky. This is a very important aspect of space research nowadays, because there's so much technology, I mean space technology, which has orbiting satellites around the Earth, and the sun can be immensely damaging. Disturbances on the sun can ultimately propagate energetic particles which, for one reason or another, reach the Earth a couple of days later and actually put Earth orbiting satellites out of operation. And health hazards for astronauts who might be in space tinkering with some apparatus, you know, the way they do, spacewalks. Astronauts could be seriously damaged by high energy radiation from the sun, gamma rays and things like that, X-rays from the sun. They're a health hazard. And knowing about space weather and what's going on in space is now very important in the whole space game. And America has set up an institute, or more than one institute, to actually make studies of these things. I decided that here was a radio astronomical technique where you could likely be able to predict when damaging conditions are going to occur in space close to the Earth. It takes 2 or 3 days for a solar disturbance to propagate from the sun to the Earth. And the Americans, using current techniques, are not able to predict the arrival of these things very easily. I thought that with radio astronomy and looking at our maps, we could probably help them a lot. And the telescope was actually working until 1994, long after it had done its astronomy, on studying space weather. But as I said, initially the survey was not designed to discover pulsars, it was designed to study radio galaxies, and that work went on for many years. I mean, it did its conventional job quietly with lots of graduate students for several years. I mean, about a decade or so. We made 2 or 3 sky surveys. It takes a long time to actually survey 900 radio galaxies at different angles from the sun, to give you all the information that you can get from scintillation, and that sky survey has turned out to be quite useful. And that, you said, you know, what happened after the pulsars? Well, they were just a flash in the pan. We worked on pulsars for a bit, but the telescope did its normal job, and ultimately I was interested, in fact still am, in space weather, using radio astronomy techniques to study space weather. It was working on that until 1994, when we couldn't run it anymore for financial reasons and for staffing reasons. Astronomy moves on, and you can't keep doing the same thing forever. I mean, that sort of monitoring of the space weather is a job not for a university research group, but for something like the Met Office on an interplanetary scale. And I was hoping the Americans would take it up. They didn't in the end. They preferred to launch spacecraft, but I still think there's work to be done there, useful work to be done by radio astronomy techniques in studying space weather that could be extremely valuable.
I was wondering if you could explain something I came across in the university website, which cites your work and pulsars, and roughly described it as the most important breakthrough in astronomy, roughly, of the 20th century.
What is the most important thing?
But why is it so important?
It opened up a completely new chapter of astronomy. The neutron stars, I mean pulsars, are spinning neutron stars which act like celestial lighthouse. Neutron stars are tiny stars which weigh typically just over the mass of the Sun. They contain as much matter, slightly more matter than the Sun, but they're only a few miles across. They're stars compressed by gravity until they're a tiny angular size. They're on the verge of becoming black holes, and in fact Stephen Hawking used to phone me up in those heady days and say how delighted he was with this discovery, because it proved that neutron stars, when you compress matter to that degree, and gravitation will do this for you in the sky, matter enters a completely new state, which is roughly like matter at a density of the atomic nucleus, but it's mostly neutrons. And these neutron stars had been predicted ever since the neutron itself was discovered neutrons were discovered in 1932. And the fact that you might get stars made of neutrons had been predicted, but no one dreamt for a second that you'd be able to detect them, because the stars are only a few miles across, and they're not particularly hot, they're not particularly violent in any way. They are totally dead stars, so how on earth would you detect them? It wasn't thought that they'd ever be detected. At any rate, the fact that we detected them opened up a new branch of astronomy. Neutron stars existed, and they opened the door to doing a whole lot of things. First of all, the study of dense matter. Matter at that density you can't make in the lab. I mean, it exists in an atomic nucleus, but you can't make a lump of it. I mean, if you could, it'd be rather dangerous, because you tend to be sucked in and so on. But they're on the verge of being black holes. As Stephen Hawking was absolutely delighted, because black holes were a bit of a joke in the late 1960s. And he was saying outrageous things about them, which we now know made his fame. But the fact that neutron stars existed meant that black holes, you couldn't really avoid a black hole. I mean, you've only got to squeeze a neutron star by about 10%, and it becomes a black hole. It can't help becoming a black hole. So it confirms that Roger Penrose, Stephen Hawking concept. But it opens up a completely new branch of astronomy, which is the astronomy of neutron stars, which is interesting in its own right. And more recently, the fact that the neutron stars are spinning and act like clocks gives you extremely accurate time measurement in space and in regions where you can actually check out theories of relativity with enormous precision. It's never been known whether some of Einstein's predictions were actually correct or not. Things like gravitational radiation, these ripples in space-time, which can't be detected yet directly. But pulsars demonstrate that these things must exist, because it was the work by Taylor and Hulse in the United States. They found a neutron star, a pulsar, which was in orbit about another neutron star. Probably a pulsar, but we haven't yet picked up the radiation from it. But pulsars, as I said, are such accurate clocks that you can use them for astronomical measurements, such as if you take two neutron stars in orbit about each other, how rapidly are they collapsing? The orbits, if the orbits are losing energy, as they must because of radiation, they'll approach each other. And you can actually measure these effects. The orbital period of two neutron stars decreases. They orbit each other faster and faster as they approach, and these effects can now all be measured. And this opens up gravitational relativistic physics, and that is a big area which led to another Nobel Prize, to Hulse and Taylor. So you see, pulsars are of importance for all sorts of reasons, but they have extended fundamental physics and astronomy, and given rise to a whole lot of new possibilities and tests, some of which are still to be made and some of which are being carried out. But it's just the most exciting area of astrophysics which happened because we chanced upon these lovely things.
Well, that's lovely. You mentioned there you were rung up by Stephen Hawking.
Yes.
If I could ask you about two of the great Cambridge astronomers, starting with Hawking. I mean, he was in an entirely different kind of field to you. He was a theoretical astronomer, but did you work with him at all, or?
No, only just to chat over the telephone. No, I mean his theories are way beyond my comprehension almost, and I like to find out what's there and let the theoreticians tell me exactly why it's there.
Well, that takes you a bit closer to Martin Rees, then, who was at least a
Yes.
evidential astronomer.
Yes.
How do you assess Martin? Because I've interviewed him, and it's nice people talking about each other a bit in these interviews.
Well, my first contacts with Martin Rees were when he was a young graduate student, and he used to come around the old Cavendish, talking about ideas about what radio galaxies might be, and I always had a great respect for him because his theories were. Well, he always talked about his sort of physics, which meant he wasn't such a highbrow physicist as Stephen Hawking. His sort of physics was the sort of physics that you can get your hands on, and his sort of physics we could appreciate, and his sort of physics led to theories of how radio galaxies work, which turned out to be correct, and he was very influential in understanding the radio maps that Martin Ryle was then making of high resolution, showing you actually what was going on in these active galaxies. And so I've always had a great respect for Martin Rees, and he's extremely clever, and I think now he's pretty wise. He used to think that astrophysics was mostly an American practice rather than the British one, but we didn't like him for that totally. But I think he's over those days now. I think he's an extremely good president of the Royal Society.
Talking of America, were you ever tempted to go to America and work there?
Not to work, no. I mean, I had some offers, but and I have had a sabbatical over there at Yale. I always enjoyed going there, but I wouldn't especially want to work there, I think. I mean, Cambridge was the centre of the universe. I don't really want to be
in every sense.
I don't want to be anywhere else.
Why was that? Why?
Oh well, everybody comes to Cambridge, don't they? And if you want to know about something, there's always somebody around you can ask. I mean, it is such a wonderful place to be. There's so much going on, and I think we're very extremely lucky to be here.
What do you put this down to? I mean, some people put it down to the college system. Do you think that helps?
That's part of it. I mean, I think history is part of it. Cambridge is a lovely place. It's sort of iconic, isn't it? And I think we attract the best people, the best young people, and they're the stimulus, and they're the pacemakers, as it were, that keep the place alive, aren't they? And I've always enjoyed our teaching methods here in Cambridge. I mean, when you give a physics course, it's something you dream up as you prepare it, but it's not like following chapters in a physics book, which is the sort of way they teach physics, I gather, in the United States. You know, they do it chapter by chapter, week by week, whereas I'd much rather try and talk about basics in the way I think about it, and you have that one-to-one contact with the young people, which I think there's less of in the United States, quite honestly.
You've done quite a lot of supervising.
Supervising and lecturing, yes. I mean, I think the combination of research and teaching is a wonderful mix. Teaching is a great challenge, especially teaching the bright young people that come up to Cambridge. And they ask you awkward questions. I don't think I ever really understood physics, although I got a first class in my final degree. I don't think I really understood physics until I taught it for 2 or 3 years. It's teaching that really gets you into the nitty-gritty of it.
And you enjoy lecturing?
Yes, I do.
Because
I mean, I'm not a publicist. I'm not an actor in any way, but it's the discipline of how do you present something. It's a challenge which I enjoy. I had to lecture the introductory physics in 1976 to anybody doing physics for the natural sciences tripos in Cambridge, so it meant that I had to, the course is now divided between those who are going to go off and be chemists or mathematicians or something. Our tripos system, as you know, is very flexible, but I had to take everybody doing physics in the first year, I'm talking now about 1976, which was about 450 students, and I had to not bore the brightest and not baffle the dimmest, and present essentially, my course was called Concepts in Physics, and teach them a lot of basic physics, at the same time introducing things that they were going to meet later on, and trying to get them used to some of the more difficult ideas of quantum physics and relativity, mixed in with standard things like Newton's laws of motion. And that was a great challenge, and I enjoyed doing that. I did that for 3 or 4 years. But I've always enjoyed the teaching side, because it is a challenge, and as you mentioned, the supervision system, that is, I think, one of the secrets of Cambridge, that close contact between people involved actively with the science and those learning it. And the questions bright students ask you are very challenging.
What about writing? I suppose you, as a scientist, you don't write too much. I mean,
no. I've been too busy, as you might say. I mean, hands-on takes a lot of time, actually, and I've never felt like getting up early in the morning at 4 a.m., to write a popular science book.
Although you're interested in popular science, you gave one of the Faraday Christmas, Royal Institution Christmas lectures.
Yes. Oh yes, well this is again this presentation. I mean, I love trying to present these exciting things to the general public. I think that's what scientists ought to be doing. I mean, after all, we're spending lots of public money, and I think it's a duty really to try and explain to the general public what it's all about.
I've just got a couple last questions, if I may. One is God. I always ask everyone about God, and whether they, particularly astronomers, it seems interesting to consider what their religious beliefs are. You mentioned going to chapel or church when you were at school, but has God played any part in your life since? Or
Yes, the answer is yes. I mean, I went through the normal teenage heretic episodes, and I didn't go to the chapel very much when I was a student, but you can't help, if you're brought up at an English public school, getting to know the liturgy and the Book of Common Prayer, and it somehow gets into your blood if you go to chapel once a day, and so I love the old music and the James Bible and all that. But I married a clergyman's daughter, and I think that was a pretty influential thing. I got to know about country parishes, and well, I've been a doubter all my life, and I suppose I still am. I do believe in God, and I believe in supporting the local parish church. I mean, I don't know if you know the Church of St Edward's, just over the road here. I was church warden of St Edward's for a number of years, until I moved out to further into the country, because my wife wanted a bigger garden, and I've only quite recently retired from being church warden of my village Anglican church in Kingston, and having thought a lot about it, and people ask you questions, of course, I think there has to be a God. I can't account for the world without a God, and to take the sort of atheist view of Richard Dawkins just seems to me to be total nonsense. I mean, I've read his book carefully, and his arguments fall flat as far as I'm concerned. They're not arguments even. Although it's a popular book. I mean, I think it's a popular book because he's saying what people want to hear, probably. But theoretical physics, you see, brings you into contact. I mean, I think science actually isn't anti-religion in any way, as I'm sure John Polkinghorne, I don't know if you've ever spoken to John, he writes elegantly about these things in a way I couldn't possibly do. But being a scientist and facing up to scientific understanding makes you prepared to believe in another world, and I can't just see the point of the universe unless there's an intelligence behind it, and so you might as well call it God. And when you look at the evidence, it seems to me the evidence is pretty strong too.
Thank you. And the last question is, if you were, and I gave this, asked this of a number of scientists, if you were giving advice to a young scientist just starting their career, say at the PhD level,
Yes.
Is there anything particular you'd say, reflecting on your own life?
Well, only the obvious, in the sense that don't follow the bandwagon. I mean, try and get into some work which is on the boundaries in some sense. When I was starting research, I was late to, as it were, apply for a research posting in the Cavendish, because I hadn't planned to be an academic, and I didn't think, and my tutors didn't think, I was actually going to do well enough in my final exam to justify my doing research, which required a first. So, and getting into radio astronomy was the best thing that could have happened to me, because all the popular research areas, like nuclear physics, like low temperature physics, like crystallography at the Cavendish, these were all very well-known areas. They'd all recruited their potential research students, and there weren't any vacancies except in this unknown area. You know, what's going on? Is it to do with the ionosphere? Is it to do with the universe? What is it? No one knew what radio astronomy was. The name didn't exist. It's just that they're looking at radio waves coming from the sun for some reason. Well, I had the technology and I could get into there and do something. But my advice is not to get into a well-worn, popular subject. Try and choose an area which looks interesting and exciting, about which little is known. I mean, at the moment, who knows, neuroscience or something like that. I mean, we haven't a clue how the brain works, really. So don't follow the bandwagon. Try and get into something where you can make your own mark. I mean, that was another great advantage of radio astronomy. I mean, I could get in and develop my own interests quite rapidly, and the technology wasn't enormously expensive or tricky. And I saw niches where I could actually make an impact. And I think when you're starting research, your first paper is about the most important paper you write, probably. And when I discovered I'd done a little bit of theory, which was really useful, I hadn't thought it was all that useful, but Jack Ratcliffe said, "Hey, you must publish that in the Royal Society." I thought, what? Me? Publish that in the Royal Society? You know, that's a tremendous boost, actually. But starting research is a very tricky time for young people. I mean, I nearly gave it up after a few months because I didn't think it was getting anywhere, to be honest. I wondered whether I'd done the right thing. So it's very iffy when you're a young graduate student, I think. But it's much easier to make discoveries in an area which is full of mystery and not much worked upon.
Well, that is so fascinating, and I want to ask you one more question, which is about, again, advising a young person on work methods. I mean, do you have your good ideas when you go for walks, or when you're having a bath, or do you pace yourself, or do you have any advice on how to think, so to speak, productively? Have you ever thought about this?
It's very hard to analyse, isn't it? No. You've obviously got to be a bit reflective. I think the ideas come to you when you're actually engaged. You want to be engaged in something. I mean, you can't just sit down in front of a sheet of A4 and write down brilliant research ideas. It just doesn't happen that way. Somehow two and two come together and click when you're lucky. No, I don't think I can give any direct advice about how you get inspiration. I'm sure different people get it different ways. But having your head in books all the time, I don't think is a good idea. I think you should give your. I mean, I think you should dream a little bit and see if ideas come.
I'll leave you with your dreams. Thank you very much indeed, Anthony. That was lovely.